real numbers, and this is a d-dimensional vector. Then yn, that is a label of the nth patient, or the label associated, or the disease associated with the nth patient, and that is always a real value r. That means we can represent that information with the help of a real value or a nominal value, etc. And here the data set can be represented in this way: xn comma yn, and this can be considered as a data pair. And this xn, the component, the first component actually represents the features, and the second component, that is y, represents the label. So the concept of a data set is very important in machine learning. So there are two types of data sets: a labeled data set and unlabeled data set. And in the case of unlabeled data set, and that is normally used for unsupervised machine learning algorithms like classification, then association rule mining, then feature selection, etc. And all these are unsupervised machine learning tasks. And for supervised machine learning task, we need a labeled data set, and a labeled data set can be represented in this way: xn comma yn. Okay, and y is the label. Then when again in order to discuss with machine learning, we have to understand these two terms, that is training data set and test data set. Then and what is training data set and what is test data set? And in order to understand the concept of training data set and test data set, first of all we have to understand the concept of universal data set. And I think all of you are aware with the universal data set. In statistics, when we consider the concept of Venn diagram, we have a universal set, say, and that universal set is always represented by using the capital letter U. Okay, but U means the all data values under consideration, and that is the concept. So universal data set, the assumption is that it contains all possible data pairs of the form x comma y, as well as their probability distributions. And probability distributions in the sense, I hope all of you are familiar with probability distributions. A number of different probability distributions are there, like binomial distribution, then Poisson distribution, then normal distribution, t-distribution, chi-square distribution, etc., etc. Okay, but here in the concept of universal data set, our assumption is that it contains all possible data members, all possible data pairs of the form x comma y, together with their distributions. Every data set follows a particular probability distributions. Then the collection of whole data plus the corresponding probability distributions actually defines the universal data set. Then for practical applications, we observed only a subset of the universal data set due to lack of memory, other unavoidable reasons, because in our computer the memory is limited. So it is not possible to store all the data available in the world. So we always concentrated on a subset of the set of data, subset of the set of data. And the acquired data set is called the training data set. That means if there exists a valid subset of the universal data set, and that subset can be considered as the training data set. That means we are going to take the inference from the training data set. Then after that we can generalize. That is, this training data set is used to learn properties and knowledge of the universal data set, and that concept is actually known as generalization. Okay, but here we have a small data set, and that is the training data set. And from this training data set, we can extract various properties and knowledge or patterns. And these patterns, our assumption is that, or our conclusion is that, these patterns or these properties or this knowledge are actually the knowledge of the universal data set. And that concept is actually known as generalization. And this is the concept we followed in the case of inferential statistics. Okay. And vectors in the training set are assumed to be independently and identically sampled from the universal set, and that is known as sampling. Sampling, that is also a concept of statistics. That means in order to build the training data set, actually the training data set is constructed from the universal data set, and by selecting the various instances independently and identically. And that the concept is known as sampling. That means with the help of a sampling technique, we can select various instances from the universal data set to construct the training data set. And in machine learning, the properties learned from the training data set actually explains the training set, and also used to predict the unseen samples. Unseen samples means, and that is actually known as the generalization. That means the knowledge obtained from the training data set can be applied to take decisions for a new unseen case. New unseen case. When a new patient came, by the knowledge extracted from an already existing data, the same knowledge can be applied for the new patient, because this new patient is an element of the universal data set. So, and our argument is that the knowledge obtained from the training data set is applicable to the universal data set also. So this knowledge can be applied to new unseen case, and that is the main idea behind any machine learning algorithm. Then, to examine the performance of learning, another data set may be reserved for testing, and that is called the test data. That is, once the learning is over, actually learning happens from the training data set, and learning is over, we have to evaluate the performance of that learned properties. And in order to measure the performance, we need another data set, and that data set is known as the test data. Okay, but here test set is unobserved during the training or learning process. That means at the time of training, and this data set is not visible to the learning algorithm. Test data is not visible to the learning algorithm. And after learning from the training data, we can submit this particular test data, and this as per the or when we input the test data into the learning algorithm, it generates some results. Then based on that results, we can measure the performance of the learned model. And in order to measure that performance, we have to reserve another small data set that is also a subset of the universal data set, and that data set is known as the test set. So this is the concept of the training data and test data. Training data is the information used to train an algorithm, and the training data includes both input data and the corresponding expected output. Expected output, that is label. Input data is there, features are there, and along with that features, label is also there in the training data. And this label is actually known as the ground truth. And based on this ground truth data, the algorithm can learn how to identify patterns to generalize the information contained in the data set, so that it can make accurate decisions when later presented with the new data. So, and here in the training data, the label is very important. That is actually that label represents the ground truth, because this knowledge is generated based on the ground truth. For generalizing the information, this ground truth information or the label is very important, and that is the reason why we preserve the label in the training data set. But in the case of testing data or test data, on the other hand, includes only the input data. That is, features are there, independent variable values are there, x values are there, not the corresponding expected output. But that expected output is available in our hand, because we can compare. We can compare after generating the output using the test data. What is the output generated, and what is the difference between the output generated and the actual data, and that can be measured with the help of the information generated. So the test data is used to assess how well our algorithm was trained and to estimate the model properties. So that means after the training, we get a model. then the performance of that model, to evaluate the performance of that model, we need a subset of the universal data set, and that subset is actually known as the test data. So the training data is used to make sure the machine recognizes the patterns in the data. That means in order to extract the knowledge, we need the training data. Then in addition to the training data, another set of data is also used for cross validation. Cross validation, that means it is actually a subset of the training data set. Then after each iteration, we have to evaluate the performance of the model at each stage of the iteration. And for that, we have to reserve a small amount of data from the training data. And that data is actually known as the cross validation data. And this cross validation data or cross valid, the concept of cross validation is used to eliminate the some undesirable properties of the machine learning algorithms, such as underfitting and overfitting, or underfitting and overfitting. These are two undesirable properties of some machine learning algorithms, and these properties can be eliminated with the help of the cross validation data. And as I said earlier, the test data is used to see how well the machine can predict new answers based on its training. That means the performance of the model, and that performance of the model can be evaluated with the help of the test data. So here, the training data and test data, these two are very important in machine learning. Training data that can be used to extract the knowledge, and once that knowledge is extracted, then in order to performance of that particular model, we need another data set, and that data set is actually known as the test data. And these are the various type of machine learning algorithms. I already said the different types of machine learning algorithms, like supervised machine learning algorithms, unsupervised machine learning algorithms, semi-supervised machine learning algorithms, and reinforcement learning algorithms. And this classification is mainly based on whether or not the system is trained with data collected with human supervision or not. And with the help of a human supervision, we collect the data, and that data is always have a particular label, because from the in a hospital, the last 10 years data, if we collect the last 10 years data, we can see that all the data elements are entered into the system with the help of some expert doctors. Okay, but here these doctors, it is the responsibility of that particular doctor to evaluate each and every patient visiting that particular hospital and assign a label. Label is nothing but the disease. And that type of data is available in any hospital. We can collect the data, and from that data, we can extract some knowledge, and with the help of that, we can take various decisions. Okay. Then supervised machine learning, because I'm going to concentrate only on supervised learning. And in supervised learning, training data feed to the algorithm is the labeled data set. And supervised learning tries to find the relationship between the feature set and the label set, which is the knowledge we can learn from the labeled data set. And that is very important in the case of supervised learning. But supervised learning tries to find the relationship between the feature set and the label set, and what type of relationship existing in between the disease and the features like symptoms, lab results, etc. And we can find out a relationship, and that relationship is actually known as the knowledge. And it is possible to represent that relationship with the help of some mathematical concepts. And if we are in a position to represent the relationship in a mathematical way, and that mathematical way of formulating that relationship is actually known as machine learning. And if each feature vector X corresponds to a label L, where L is equal to L1, L2, L3, etc., Lc, and C is usually ranged from 2 to 100, the learning problem is called classification. That means for each feature vector, and corresponding to that each feature vector, if we are in a position to map a particular label to that feature vector, then the problem can be considered as a classification problem. But here, if we have only two different classes, for example, if the disease, if the patient, again, if we consider the details of a patient database, and if the data set contains the information related to COVID-19 patients, whether that particular patient affected with COVID-19 or not affected with COVID-19. Okay, and that type of problem can be considered as a two-class problem. Okay, but here L contains only L1, L2. L1 is the first class and L2 is the second class. But in general, here we have so many classes, and C usually ranges from 2 to 100. And in that case, as a classification problem. That means here from the data set, if we consider any instance from the data set, that instance can be mapped onto a particular label. So the problem is a classification problem. And a spam filter is a good example for a supervised machine learning task, that is classification. And it is trained with many example emails along with their classes. And class means this can be considered as a two-class problem. That is, the mail can be a spam email or a ham email. And here we have a data set. This is the training set. And this training set contains the characteristics of various emails along with the corresponding label.
അതൊന്ന് ക്ലോസ് ചെയ്തേ അച്ചു അത് ക്ലോസ് ചെയ്യും ഇവിടെ
we can find out the relationship existing in between the various features and the corresponding label, and with the help of that relationship, extracted relationship or extracted knowledge, we can take the decision regarding when a new email came, whether that email is a spam email or a ham email. That decision can be taken by using the relationship extracted from the training data set. And that is the idea behind any type of classification algorithms. That is, we can provide a training data set, there is a labeled data set, and from that labeled data set, we can extract some relationship existing in between the features and the corresponding label. And this relationship can be used for taking the decision regarding a new email. When a new email came, we can check whether that email is a spam email or not spam with the help of the learned relationship. But here, if each feature vector x corresponds to a real value, that is y belongs to R. In this case, y is not a real value, spam or ham. That is the label that can be given in this case. So this is not a real value. In some cases, the label may be a real value. Then, if the label is a real value, the learning problem is defined as the regression problem. As an example, to predict the target numeric value, say price of a car, given a set of features like mileage, age, brand, etc. That means we have a data set representing the details of some cars, and these are the features like mileage is one feature, age is another feature, then brand is another feature, the number of features are there. And if we provide these features to our machine learning model, this machine learning model generates a real value, say price of the car. Then in that case, the problem can be considered as a regression problem. But in our previous problem, this is not a regression problem, this is a classification problem. So classification and regression, these are two important important components in machine learning. Okay, supervised machine learning, classification and regression. But here, this is a classification problem. But if we consider this particular problem, this is a regression problem because the label is a numeric value, not a categorical value. The knowledge extracted from supervised learning is often utilized for classification and prediction. And note that some regression problems can be used for classification as well, and vice versa. Because here, when we consider the simplest machine learning algorithm, that is linear regression. Linear regression is a regression problem. But this linear regression can be modified to classify some emails. And in that case, that classification can be considered logistic regression. Logistic regression is a classification algorithm, and it is a modification of the linear regression. Here, that is the difference between regression and classification. Classification is always associated with some categorical values. Labels are categorical in the case of classification, but in the case of regression, the label is a numeric value. Label is a numeric value, and in some cases, the
But
regression problem can be modified to handle the classification.
Srija, please mute. Srija, one of the participant, please mute.
For example, logistic regression is commonly used for classification as it can output a value that corresponds to the probability to a given class. That means in logistic regression, we can generate a probability. Even though it is a real value, it can be considered. For example, 0.2 is the value generated by that particular regression algorithm. And with the help of that real value 0.2, we can classify the email. That means there is a 20% chance that this particular email may be a spam email. Okay, and some of the popular supervised learning algorithms are linear regression, logistic regression, support vector machines, naive-Bayes classifier, then decision trees and random forest, neural networks. A number of other algorithms are also available. And in today's lecture, I'm going to implement the naive-Bayesian classification algorithm. And for that, in order to implement the naive-Bayesian classification algorithm, we have to understand, or we have to study some basic information related to statistics like probability. That is one basic concept, probability. I think all of you know the concept of probability. Here the definition: consider a random experiment having n outcomes, and out of these n trials, an event A happens f times. And when we consider a random experiment, then the total number of outcomes can be considered as the sample space of that random experiment. I think all of you know the concept of a random experiment. Then out of these n trials, an experiment A happens f times. So A can be considered as an event. An event A happens f times. Then f by n is the frequency ratio of the event A. So based on that frequency ratio, the probability of that event can be defined in this way: P of A is equal to limit n tends to infinity f by n. And that is the actual definition of probability. So probability is always associated with a random experiment. Every random experiment is associated with a sample space. Then a subset of the sample space is known as the event. And here that event can be represented as A. Then f by n is the number of outcomes of the sample space. So f by n, and that is the frequency ratio of the event A. Then probability of A is equal to limit n tends to infinity f by n. Or simply, P of A, the probability of the event A is equal to number of favorable cases divided by total number of outcomes. And that is the simplest definition of the probability: number of favorable cases, how many times they happens, divided by total number of outcomes. And this concept is very important in machine learning. The next, once again, to understand the concept of probability, the best example is flipping a coin. There are two possible outcomes. That means sample space contains only two outcomes, head or tail. And what's the probability of the coin shows the head when it is tossed? And all of you know, you can compute that probability. And what is the probability of the coin shows head when it is tossed? And here head happens only one time. And how many sample spaces are outcomes are there? 2. So the probability is 1 by 2. That is 0.5. And again, another very important information is that the probability of an event is a number always lies in between 0 and 1. The probability of an event is a number always lies in between 0 and 1. 0 and 1. And this is the basic information associated with the concept of probability. And I think all of you know now the concept of probability and sample space, event, then frequency ratio, then the definition of probability. Definition of probability. The next very another important basic concept is conditional probability. Conditional probability. Again, I think all of you know the concept of conditional probability. The conditional probability of an event A, given that another event B has occurred, is denoted by P of A given B, and is defined as P of A given B is equal to P of A intersection B divided by P of B, where P of B not equal to 0. And this is a basic definition. I don't want to discuss more on this particular definition. I think all of you know the concept of conditional probability. But here, in the case of this conditional probability, P of A given B, the information regarding the event B, that is known to us. Based on that known information, how can we compute the probability of another event A? So probability of A given B is equal to P of A intersection B divided by P of B. And when we consider a Venn diagram, this is the representation of A intersection B. So this is A and this is B, this is A intersection B, and this can be represented as B intersection A complement, A intersection B complement, and all these informations we studied in our high school classes. Then, and with the help of this conditional probability, to understand the basic concepts of conditional probability, we can consider a very simple example. If a pair die is tossed, then what is the sample space? Sample space S is equal to 1, 2, 3, 4, 5, 6. Because 6 different phases are there in a die. Let A be the event that the outcome is an odd number. Okay, then A, what are the possible cases of cases corresponding to this event A? That is 1, 3, 5. Because the event A is the outcome is an odd number. That is when an odd number comes, then that can be represented as the event A. And these are the possible cases 1, 3, 5. Also, let B be the event that the outcome is less than or equal to 3. Less than or equal to 3. That is B is equal to 1, 2, 3. 1, 2, 3. Then and here we can I would like to ask two questions. And what is the probability of A? Then the second question is, what is the probability of A given B? What is the probability of A given B? Then, as per the definition of probability, what is probability of A? Number of favorable cases divided the total number of outcomes. And here, P of A, the number of favorable cases, that is the cardinality of A divided by cardinality of S, where S is the sample space. Then what is the cardinality of A? How many possible cases are there? In the case of A, 1, 3, 5, that is 3. That is the number of possible cases. Total number of outcomes, the total number of different information contained in the sample space. That is 1, 2, 3, 4, 5, 6. So 3 by 6, 3 by 6 is 0.5, and that is the probability of A. Now, let's find the conditional probability of A given that B has occurred. Given that B has occurred. And if we know B has occurred, the outcome must be among 1, 2, 3. Okay, because B is even B is defined as an outcome with less than or equal to 3. Less than or equal to 3. So for A to also happen the for A to also happen, the outcome must be in A intersection B. That means A and B simultaneously should occur. Then in that case, A intersection B is equal to 1, 3 because A is 1, 3, 5 and B is 1, 3, 1, 2, 3. So A intersection B is definitely 1, 3. Then and here all the outcomes are equally likely. All the outcomes are equally likely. That means the chance of occurrence is same for all the different outcomes. All the different outcomes. So in that case, probability of A intersection B, as per the definition of probability of A given B, it is the cardinality of A intersection B divided by the cardinality of B. That means how many outcomes are there in A intersection B? Only two outcomes. Then how many outcomes are there in B? In B, the outcomes are 1, 2, 3. So 3 outcomes, therefore 2 by 3. So probability of A given B is equal to 2 by 3. And this A given B is nothing but this information is available in our hand. The information regarding B is available in our hand. Based on that, we can take the information regarding another event A, and that is actually P of A given B. And in this case, P of A given B is equal to 2 by 3. In this way, we can solve some simple problems related to conditional probability. A number of other problems are also there. Then, next, we can move on to another very important basic concepts of probability, that is Bayes' theorem, because this is a very important concept in probability theory. Bayes' theorem was named after 18th century mathematician, that is Thomas Bayes. And Bayes' theorem relies on incorporating prior